Hello there. In this lesson, we're going to take a closer look at single displacement reactions. These are the ones where you have a compound and an element, and the element takes the place of one of the elements in the compound. In this example here, we have some copper wire, and in here we have some silver nitrate solution, right? And as the reaction proceeds, you can see that now there's some silver that is precipitated out, and in the solution now you have the copper ions. That's the blue color. So when there's a switch like that where one is taking the place of the other one, that's called single displacement. So here it is as an equation. You can see that the single element here is going to be displacing or taking the place of another element in the compound. So this can work with metals and nonmetals. So we'll spend most of our time with metals, and there's a few nonmetals that we'll look at as well. Oftentimes the compound is dissolved so that you can actually see a new metal being formed as the reaction goes on, like you saw on the previous slide there. And so it's pretty easy to work out what the products will be. You just find the element that is on its own, and you bump out the similar element in the compound. So this is a metal, so I'm going to take out the metal in this compound. So we're going to end up with the magnesium with the chlorine, and that's the new compound. And the other product is going to be the zinc all by itself being displaced. So in order to determine whether or not a single displacement occurs, we're going to use what's called the activity series. And basically it's just a list of elements in order of reactivity, with the ones at the top being the most reactive, and they can displace everything below them. And the ones that are lower down, they cannot displace those that are above, right? So you can displace things that are below but not above. So using the list, we can see that we have barium and sodium here. Where's barium on this list? There it is, barium and sodium. There's the sodium. So the barium's above sodium, so that means that we'll end up with some barium chloride, which is the barium displacing the sodium, and then you end up with the sodium all by itself, and that would be the displacement. If we tried the reverse reaction, if we took a piece of sodium and stick it in some barium chloride, there'll be no reaction because the sodium is below the barium on the activity series. So you'll see that hydrogen is also a part of this activity series that includes mostly metals. So hydrogen follows a few slightly different rules. As you can see on this list, there's an awful lot of metals that are above hydrogen. And as long as hydrogen is in an acid, well, then they can all displace it, right? Can all displace it. So magnesium with hydrochloric acid, so there's the hydrogen, the magnesium can displace it, and you'll get magnesium chloride, this time aqueous, and some hydrogen gas, right? That's the way hydrogen is as an element. So to balance it, you need a 2 there, and then you're good. Copper is down here below hydrogen on the activity series, so that means that you'll get no reaction here. So hydrogen and water follows a little different pattern. Not all of the elements above hydrogen on the activity series can displace hydrogen from water. The cutoff is where magnesium is. So only these guys above magnesium, on my list it's only 3, but there are other lists, can displace hydrogen from water. And then all of these, all the way down to lead on my list, can displace hydrogen from acid. And when it does displace hydrogen from water, it's a little different. You can think of water as being like a hydrogen and a hydroxide, right? 2 H's and an O. So when the sodium comes in here, it's going to displace just one of these H's, and you end up with an OH that's left behind, and that's what bonds with the sodium. So you end up with NaOH as the compound that is formed, of course still dissolved, and H2, the gas, those are the bubbles that will come off as well. So you'll end up with a base whenever you do a metal displacement of hydrogen from water. because all your hydroxides are bases. Zinc is below magnesium on our activity series, and so there'll be no reaction for that. All right, the last type of displacement we're going to look at here is with halogens. So halogens, as you recall in the periodic table, is group 7, and it turns out that the order on the periodic table is the same as the activity series order. So FClBrI, FClBrI, and it works the same way. Fluorine being at the top of the list, it can displace all the ones below it. Iodine at the bottom can't displace anything above it. So if we have a look here, we got bromine displacing sodium or chlorine. Since bromine's the nonmetal, it can displace the chlorine part. And bromine, bromine's actually below chlorine, so we got no reaction for that one, no reaction. Then if we have fluorine trying to displace the bromine, well, that will react because fluorine can react with bromine. And so that means we're going to end up with sodium fluoride, which is in your toothpaste. And you'll also end up with some bromine liquid. When you are writing out your new elements, of course, don't forget Hofbrinkel, bromine, and all your other halogens are all part of the Hofbrinkel group, which always come in pairs. And so that's important for balancing things out. So we'll need 2 here and 2 here to balance that. So a couple neat single displacement reactions that you might have heard of, or if you haven't, we'll share them now. One is called the thermite reaction. Thermite reaction is very energetic. It's when you have some aluminum and some rust. And so I have this pair of old steel ball bearings, and on the outside of them there's some rust. Fe2O3, that dark stuff you see there, that's a little bit of rust. And then this is just some aluminum foil that's been wrapped around another ball. And when you bash them together, you get this cool reaction where a lot of energy is given off, and it makes this cracking sound. And what happens there is it produces a little bit of iron metal, and you get some aluminum oxide as the other product. Another neat place where it's used is in extracting iron right out of the earth. So when you dig into the earth and you find a place that has iron in it, it's usually as iron oxide. You don't really find a lot of pure iron out there because it reacts so readily with oxygen in the air. And so what they do is they heat it up and they put some carbon in there, usually powdered carbon, in with this molten ore from the earth. And you'll end up producing carbon dioxide, which just sort of bubbles away, and you end up with pure iron remaining when you're done, which is what we use for a lot of things in our society. All right, so one last thing that we're going to learn about here is when you take a little closer look at the charges of elements in a single displacement reaction, you see that the charges change. And so a way to see that would be to separate any of the aqueous solution compounds into their ions. So silver, in silver nitrate, it has a positive charge, and nitrate has a negative charge, and then the copper is sitting there and it has no charge, right? So the two here, they have a charge and the copper doesn't have a charge. Then after the reaction, we got copper as part of this compound. Copper has this 2+ charge, and then nitrate still has the negative charge, and now it's silver with no charge, right? So this is solid, this is aqueous, this is aqueous. So that's what's going on in our original reaction that we were looking here. We made this silver solid, it's the flaky stuff you see there on the outside of this copper wire. And so you can see that the silver went from having a positive charge to being neutral. So to do that, it had to gain an electron, right? Gained an electron. And you can see the copper here went from having no charge to having a +2 charge. So it lost 2 electrons. So in any single displacement reaction, there's some electrons being transferred to make it happen. And this is sort of unique. There's a whole class of reactions. I'll learn more about them in grade 12, but it's kind of unique in this in our course this year to have reactions that where the electrons switch spots. And so I'd just like you to be able to identify that we have electron switching spot. You can even just count how many it's going to be. If you go from a 0 charge to a +2 charge, that's 2 electrons. And if you have positive and you come back to neutral, that's just 1. Okay, so here's another one. Let's see if we can figure out where the electrons are going here. If you don't want to write out the whole ionic equation, I will again. You can just stick the charges right on if you want. This one has a +2 charge, and this has a -1, and it's a +2, and this is a -1. And so you can see, again, with magnesium here with no charge and zinc here with no charge, you can see that the zinc here became zinc with no charge. So how do you do that? You had to add some electrons, 2 electrons. And here you got some magnesium, and magnesium became magnesium with a 2+ charge. And so to do that, you had to give off electrons. So all of our single displacement reactions will have this. They'll have electrons being given and taken throughout the process. And so I just want you to be able to identify them, which ones are switching. The ones that go from 0 to a positive charge, they had to do that by giving up electrons, and the ones that go from a positive charge to 0, they have to gain electrons. Last thing here is that when you write out an ionic equation, you'll see that there are some parts of the equation where there's no change. So we'll do this one again. Chlorine is not dissolved, but the magnesium here, it's dissolved. And the bromine here, also dissolved. There's 2 of them. And you go to the other side, the magnesium dissolved. And we've got 2 chlorines that are dissolved. And you've got the bromine that is not dissolved. And so you can pick out again which ones are changing their charge. You went from a 0 here to a -1 over here. So you can say that the chlorine gained an electron, right? And you can notice that this bromine here became bromine with no charge over here. And so to do that, it must have given up an electron, right? So you can work out the ones that changed their charge, and that's really the reaction. But you can see here that magnesium didn't change at all. Before, it was magnesium with a 2+ charge floating around, and after is also magnesium with 2+ floating around. So anytime there's an ion in there that doesn't do anything, that doesn't change, we call that a spectator. And really, it was in the solution floating around, not doing anything the whole time. If you, say, evaporate all the water off, perhaps it would bond with the chlorine ions that are there. But for now, it's not doing anything, so we call it a spectator ion.